Hello, my name is Craig Beasley and I'm Vice President of Exploration for NEOS Geosolutions. This presentation, entitled High Grading Minerals in the Great Basin, will present results from a NEO-prospector survey that NEOS recently conducted on behalf of U.S. Gold. The exploration approach was to conduct a NEO-prospector survey consisting of hyperspectral, magnetic, radiometric, and electromagnetic techniques. The project begins with analysis of publicly available information such as the USGS geologic map of Nevada shown on the left. Within the project area, the client target is a sediment-hosted gold deposit. Stratigraphic units hosting gold mineralization are both exposed and covered by non-mineralized geologic units. Shown here is an aerial image of the project area. U.S. Gold provided detailed proprietary information for the area within the inset polygon, and NEOS conducted the NEO-prospector survey over the extent shown by the outer black polygon. As shown in this slide, the USGS geological map of Nevada does not provide adequate detail within the project area to do a rigorous assessment of the geologic units and hence the target potential within the project area. Fortunately, geologic mapping conducted by U.S. Gold provides insight into the geologic units and structural context within the project area. Key gold-bearing Devonian carbonate units are present within the project area. U.S. Gold also conducted ground-based geochemical surveys. Shown here are gold, soil, and rock chip geochemical values. These proportional symbol plots illustrate the relative distribution of gold at the surface. When exploring for gold, it is important to look at other indicator minerals within the geochemical data set. Shown here are the proportional symbol plots for gold along with the proportional symbols for arsenic, mercury, and antimony. Drilling on the property to date has allowed for the generation of a subsurface gold volume. Surface projections from different grades are shown in this plot. The .003 ounce per ton shell is shown as a black polygon, while the 0.03 ounce per ton shell is shown as a magenta polygon. Moving on to the NEO-prospector data that were collected, this slide shows an image of the hyperspectral data. Hyperspectral data are collected across a broad spectrum which allows for both mineral and lithologic discrimination. Shown here are mineral classifications derived from the hyperspectral data. The high-resolution hyperspectral data also yields detailed structural analysis, allowing for faults and lineaments to be well identified within the hyperspectral datasets. Magnetic data are also collected as part of the NEO-prospector data suite. This reduced-to-pole magnetic image identifies volcanic rocks in the eastern portion of the survey area via high amplitude data and carbonate rocks in the western portion of the survey area via low amplitude data. It is advantageous from an interpretation standpoint to compute a reduced-to-pole residual data set. This data set provides enhanced resolution of magnetic features, particularly in the areas of low amplitude data. Computing derivative products provides further enhancement of the magnetic features, as illustrated here in this image of the reduced-to-pole vertical derivative. Resistivity data are computed from electromagnetic measurements conducted at multiple frequencies. The depth of penetration is dependent upon the frequency of data collection. Shown here are resistivity data computed from 32 kilohertz electromagnetic data. Variations in the resistivity data reflect different lithologic units within the survey area. This image shows resistivity data computed from 4 kilohertz electromagnetic data. Note the variation in resistivity as a function of depth between this image and the previous image of the data collected at 32 kilohertz. Progressing deeper into the subsurface, these resistivity data at 450 Hz illustrate the direct correlation of high resistivity material with gold. Looking deeper still, our total divergence data shown here that illustrate distinct lineaments and relationships between the gold distribution and the edges of conductive and resistive features. Radiometric data are also part of the NEO Prospector toolkit. Shown here are total count data, which can be decomposed into individual potassium, uranium, and thorium radioelement datasets. These datasets are important for both lithologic and alteration mapping. So far, datasets have been presented, but it is also important to analyze true three-dimensional physical property models. A three-dimensional lithologic volume has been computed from the drill hole database provided by U.S. Gold. Also shown here are subsurface gold values greater than 0.003 ounce per ton gold. A three-dimensional magnetic susceptibility model has been created from the airborne magnetic data, while a three-dimensional resistivity model has been created from the airborne electromagnetic data. Having these three-dimensional models allows for a rigorous assessment in 3 dimensions of the various model sets relating to the various physical properties and mineralogic and geological units in the subsurface. As part of the NEO Prospector interpretation process, probability distributions are computed utilizing all available data sets. Shown here is the database probability distribution for gold. Given that NEOS has computed data sets in the subsurface, it is possible to compute probability maps in a three-dimensional sense. This image shows a gold probability map at a depth of 50 meters. Continuing the process, this slide shows the gold probability map at a depth of 100 meters. This process is repeated at a suite of depths so that NEOS is able to compute the probability of gold distribution across a series of depths and lets the interpreter assess how the gold distribution varies as a function of depth. Shown here is a gold probability isosurface along with existing drill holes and subsurface gold. An analysis of this information shows yet to be tested high priority target areas ripe for step-out drilling. Through a systematic and detailed interpretation of the NEO Prospector data, NEOS has been able to provide an integrated, fused interpretation to U.S. Gold, identifying key priority target areas. Through this process, high-resolution multi-parameter data sets and 3D physical property models provide surface and subsurface geologic information. These NeoProspector products are readily fused with proprietary client data sets. The fusion of NEOS and client data and model product yields 3D probability volume, identifying new high-priority target areas. As a result of this project, the client has been able to tune an exploration program to align with this interpretation, results to be determined. They are looking at expanding the regional coverage via a neo-basin survey and scoping neo-basin surveys in other mining provinces outside of this particular area. In this final slide, a proposed neo-basin survey within the Cortez Trend is shown. The neo-basin approach allows for a cost-effective, systematic assessment of a large tract of ground by applying hyperspectral, magnetic, and gravity measurements in conjunction with other available information to allow clients to fully assess in a regional context the geologic potential within a broad exploration area. Thank you very much for attending this presentation on the application of a NeoProspector survey to a gold exploration project in the Great Basin, Nevada.